Yeah, here, this binary tree, I want to show you what's the meaning of this near complete binary tree. Yeah. You know complete binary tree. So all the levels must be full, complete binary tree. So near complete, because you can draw near complete binary tree in many different ways. Here, what we mean is, other than this bottom level, because the bottom level may not be full. Yeah. The reason is simple. For complete binary tree, the number of nodes must take this form, 2 to the k minus 1. Then you can draw a complete binary tree. If n cannot be written in this special form, then you cannot get a complete binary tree. If we cannot get complete binary tree, we arrange the nodes. We try to match the complete binary tree, but at the bottom level, we just put all the remaining elements in the bottom level. Yeah. So you can imagine we fill first level, second level, each level the best we can. Then at the bottom level, we just put the remaining elements in that bottom level. So then we get a near complete binary tree. Then for any n, not necessary 2 to the k minus 1, any positive integer n, we can arrange the elements in this near complete binary tree. All right. Then, sufficient space for dynamic, that's another important technical consideration we need to consider. So what's that? Sufficient space for dynamic data. Because the data is dynamic, then you do not know the exact size of the data, right? The size of the data. The size can change. Your data can grow. When the data is growing, how do you manage your storage space to hold all of your data? That technical question, you need to have some solution. Yeah. So we need to think about possible solution for this number 3 technical requirement. All right. Then number 4, certain relationship among nodes. That's the definition of parent-child relationship. Number 4. But number 3 is a challenging technical problem to be solved. I will talk about the idea later. All right. How much space is sufficient? So let me explain how to get sufficient space. It's hard to predict. At the beginning, it's very, very hard to predict how much space is sufficient. We cannot. Nobody can do that. So we need to use a special way to adjust the array, the size of the array we use to store the data. Yeah. All right. So when the data grows, that requires more storage space, we need to make our storage array larger. When the data shrinks, the size is reduced significantly, then we need to reduce our storage location. Yeah. But usually people talk about growing. Yeah. Data growing is more common than data shrinking. Shrinking is rare. It's possible, but very rare. Yeah. Most common situation, data keeps growing. Yeah. All right. Here, let me explain the data. How do you change our storage array, the size of the storage array, to make it hold the growing data? All right. At the beginning, it is unknown. Yeah. Nobody can predict how large do we need to store the dynamic data. Yeah. All right. Then, so you need some initial storage space. When you start, so you need to allocate certain amount of data, certain amount of memory space to store the initial data. All right. Yeah. After that, the data keeps growing. New data items come in, keeps growing. Then sooner or later, the allocated space may not be enough. So you need to enlarge your array size. All right. Yeah. So here, the question, how to enlarge the array size? Yeah. All right. So let us recall our array a little bit. The property of, basic property of array. The basic property of array. Right. The first one, fixed size. When you create an array, the size is fixed. You cannot change its size. But sometimes people want to change the size of the array. If you really want to change the size of the array, what you can do is you need to create a new array with larger size. Then copy the data from the old array to the new array. Then you destroy old array. That's the only way you can enlarge your array size. But you cannot change the size of your old array. So that's its property. Another property of the array, all the elements of an array must occupy consecutive location. In memory. Must be, consecutive location. So you cannot skip some of the locations, all consecutive locations. So that means when you delete an old data item, after deletion, you cannot leave one location unoccupied, vacant. So you need to reorganize the data in the array. to make all the elements occupy consecutive locations. Otherwise, you have problem to, you may access the wrong data. Yeah. So those properties you need to know in your mind. So when you design new data structure. All right. Then, now I want to explain the ideas how to make dynamic array to hold dynamic data. So our storage space, our storage object array, it is a dynamic array. Conceptually, it is a dynamic array. But remember, we use new array to replace old array to make it dynamic. We cannot change old array to make it dynamic. So we need to create a new array to replace old array to make it dynamic. All right. But there is another important technical consideration is data copy. When your data size is very large, when you do data copy, it is very expensive. So that problem you need to factor in. Data copy. Think about from old array to new array, but your array size is very large. For example, 1 million data items. You copy an array with 1 million elements to another array with more than 1 million locations. How much time you need? We know data copy, small amount of data copy is very fast. But for large data size copy, it could be slow, relatively slow. Think about if you need a few seconds, let's say 3 seconds, data copy, you copy 1 million elements in an array to another array. If you need 3 seconds to complete that copy operation, think about how your customers feel. Because when you do data copy, you cannot do anything. You cannot do anything. The program has to stop. The program has to pause there, waiting the data copy complete before you can do the remaining part of the work. But that 3 seconds pause, it is very long. From the user's point of view, it's too long. Waiting 3 seconds, pause 3 seconds. The experience is very bad for that long waiting. Too long. So you need to change your algorithm to eliminate this 3 seconds pause. Here, let me describe a simple idea. How to eliminate this long 3 seconds pause time for your customers. All right. Here, I use this diagram to show the time used, CPU time. So this curve represents CPU time. Okay, all right. Then for this peak part, that's the data copy. When you do the data copy, CPU need to, yes, most of your CPU time is used to copy data from old array to new array. Then, other parts of the program have to pause. No data processing, because the storage part need to be fixed first before you can work on the normal jobs. All right, so this is a big bottleneck. The data copy part is a big bottleneck when you double your array size. Because so here, how to enlarge the array. Enlarge the array. The usual way people double the size. When the current storage array is run out of space, then you create a new array that doubles the size of the old array. Double the size. Then you copy the data from old array to new array. All right. So in that situation, how to remove this peak? So we want our goal. We need to modify our algorithm to remove this peak. So the idea is like this. All right. We want to spread out. Because the duration of this data copy, short period of time, right? 3 seconds, remember? In 3 seconds, we need to complete the data copy. Now our idea, we spread the data copy to a much larger interval. We spread it, but then in each instance, data copy occurs in all the instances in this interval. But the CPU time used for data copy controlled relatively small. The CPU time used very small. Then the CPU can still work on other things. CPU still has, a lot of CPU time can be used for other data processing. Things like that. Okay? Yeah? So if we can implement this idea, then, because the delay, so if you consider the delay just, a few, let's say 3 milliseconds, for example. Because every time we just copy small number of elements from old array to new array. So then the waiting time, like 3 milliseconds. Then our customers cannot notice the difference, right? Waiting for 3 milliseconds, no difference, no waiting time. So in that way, we can cut off this peak long delay. So our customers will not feel any difference. Okay? Always do the normal work. All right. Let's specific how to implement this idea. Here, let me give you, simple description here. How can you make that happen, right? How can you spread the CPU time in a short period duration, 3 seconds, to much larger interval? Actually, the implementation is also pretty simple. Let me explain the high-level idea about this technical problem. How to copy big arrays gracefully. All right. Copy big arrays gracefully. We know when you copy an array of data items, if the array size is very large, you may need quite some time to complete the data copy. So that amount of time, although if you look at the absolute time number, it may not be a big number. So I mentioned, for example, about 3 seconds. Yeah, because our computer is very powerful. You can imagine it's reasonable to think about you may need 3 seconds to complete data copy. But this 3 seconds delay is very bad from your customer's point of view. That experience is very bad. Now, we want to find a smart way to do the data copy without much delay. When you do the data copy, definitely you need to use the CPU time, right? But you spread the usage of CPU time in a relatively long period of time. In every instance, you only need 3 milliseconds to do the small data copy. And in the whole long period, you complete the whole big data array copy. Yeah, here, let me give you the technical details, mainly the high-level idea. All right. First, when we start, your array has a capacity, right? Yeah. So your array has certain number of storage locations to hold your data. Here we set the threshold, appropriate threshold. How large is the threshold? We set 90% of the capacity of the array. Yeah. Here we have two concepts we want to separate. One is array size. Array size, that's we refer to the number of locations occupied by our current array, the data part. Capacity, the available total locations in the array. So you can imagine, suppose this is our array. Okay? So we have a lot of storage locations. But when we use it to store the dynamic array, so we use part of it, right? So the current array occupies this many locations. Then that's the data size. Then we have some more room to be used to store further incoming data items. But eventually, all the locations will be occupied. When the array is full, then we need to make the data copy. We need to create a new array. Yeah. So here, full. Yeah. sooner or later your array is full, so then we need to create a new array. The new array with double the size of the old array, or double the capacity of the old array. Double it. So there, we have plenty of room to store new incoming data items. That idea. But when you do that, make the data copy. So we use this simple idea. The idea is very simple. All right. Yeah. So after this 90% line, so we, in our program, we monitor the data size and take the ratio with the capacity. When it reaches the 90%, then it triggers the data copy action. Triggers data copy action. Okay, all right. So data copy starts as soon as the size reaches 90% of the capacity. Yeah. After that, new array created with double size, then start the data copy. Yeah. Now think about there are 10% of the capacity remaining, right? Yeah. Yeah. So we use the remaining 10% to hold new incoming data items. But now we do copy in this way. When a new data item comes in, we do 10 old data item copy. 10 old data items copy from old array to new array. So here you can see that's 1 to 10 ratio, right? 1 to 10 ratio. Then, because we have 10% remaining of the capacity we can use in the old array. So you run your regular operations when you use the remaining 10% of the space. All right. You will use it up, right? Yeah. But when you use it up, 10%, remember, it takes some time to use it up. Remember, we do 1 to 10 ratio copy, 10 times 10%. Our data copy efficiency, it will be 10 times of the amount of data copied with respect to the incoming new data. That is 100%, right? That means when you use up the remaining 10% of the space, you copy 100% of the old data in the array. Completely you copy it into the new array. The new array becomes double the size, right? So in the new array, you have occupied half of the size already. But remaining, you have another half you can use to hold the new data. Things like that. This kind of idea. Think about it. Yeah. All right. Yeah. So let me complete this topic. We move to the next topic. Yeah. So this is currently it's an important task we need to do. Yeah.
how to store a binary tree in an array, how to define parent-child relationship. All right. So here we need to imagine a binary tree in an array. Yeah. Actually, there is no binary tree inside an array. Yeah. No concrete binary tree inside an array. Yeah. But we may put an imaginary binary tree inside an array. All right. How to make that happen? Yeah. So we can control array elements by array indexes. Each array element corresponds to one node in a binary tree. One node. So we use array indexes to control the nodes in this binary tree. That's very convenient. Right? But how to define relationship between two nodes? One parent, one child. Here, we want to use a simple way. So very simple, but very effective way. All right. Now, the definition of parent-child relationship. Here, I draw this triangle shape nodes, 3 nodes. P, that's the parent node. L, left child node. R, right child node. Array indexes. In an array, we can only use array indexes to access different array elements. Parent node, we assume the index is I. Then, which node, which element we want to use as the left child node? The element with double the parent index number, 2i, double it. Right child, 2i plus 1. Very simple. So we use this simple math formulas to represent parent-child relationship. So simple, yeah. But we need to check if the simple method works or not. Yeah. So let's check a little bit. All right. First, the parent index I cannot be 0. Otherwise, when you double it, you get the same number, right? 0, double, you still get 0. So we do not allow I equal to 0. That means the first element in the array cannot be used as a node in our binary tree. That's okay. Only one element, right? So we can take it. Only one element difference. It's not a big deal. Then all the remaining elements we can use to represent nodes in this binary tree. All right. Second, regarding the coverage, if we use the indices in this way, can we cover all the locations excluding the first element, index 0 element? That one, we do not need to cover it. So in this way, can we cover all the locations? Because we don't want to waste, right? Waste a certain number of locations in the array. Answer is yes. Because double even numbers, 2i plus 1 odd numbers, so we can cover all the locations in this way. Yeah. So we do not miss anyone, yeah, other than this 0 location. So it looks like this method should work well. Yeah. Yes, actually, it's a simple, easy way that allows us to define parent-child relationship. Yeah. All right. Yeah. Then, two types of heaps. Next, we need to work on the ordering inside this heap. We need to arrange the elements based on the order, right? Greater than, less than, that order. Order information is important. So now we need to consider two types of heaps. One is called max heaps. The other called min heaps. Maximum, minimum. The meaning, so you start from the maximum element on the root node in the binary tree. The root node is max, then you get a max heaps. Then the root node stores the minimum, then you get a min heaps. But there are other properties. Okay, other property. All right. Max heap property. The max heap need to follow this max heap property. What is the max heap property? This is max heap property. A of I, array element. We assume we use capital A array to store this heap. The value of A of I, parent node, right? Value corresponds to the parent node, should be greater or equal to the value of its left child node. A of 2i, that's the value of its left child node. And also value of the parent node is greater or equal to the value of its right child node. Yeah, that's simple. Right, yeah. Min heap, you just change the direction of these two inequalities. The opposite direction. So you maintain that min heap property. So these two types of heaps are symmetric. So when we flip, okay, change the direction of equality, then we get the other case. So here we only need to discuss this max heap case. All right. Now, let us look at one max heap example. How to store a max heap in an array. Look at this binary tree. So the index values, these are the index values, 1, 2, 3, consecutive indices. Inside circle, that's the values of the array elements. All right, 16, the largest value of the array elements, so we put it at the root node, 16 in the root node. Then, two child node, left child 14, right child 10. Both less than 16. Remember, it follows the max heap property. For each triangle, when we examine each triangle, it must follow the max heap property. The value 8 and 7 both less than value of parent 14, and so on. So everywhere. So this is a valid max heap. Right. So you see a visual binary tree organized in this max heap structure. Next, we need to store, because this binary tree, that's in our imagination, right? The underlying storage array, we cannot store this kind of visual object, visual binary object, right? Yeah. So inside array, we still use our normal storage way. Yeah. The first location, we leave it blank. Yeah. First location, we cannot store any node in this binary tree. Then, the root node 16, location number 1. Then 2 child nodes, left child, right child, location 2, location 3, 14 and 10. Then another, so location 5, 4 and 5, 2 child nodes for the node number 2, and so on. See? Yeah. So you can see we can organize our binary tree structure in a perfect way inside an array. Yeah. So that's the way we use to represent a binary tree inside an array, specifying parent-child relationship. Very simple. Here you can see there is no pointer used, right? No links used. So the hidden connections among different nodes, we use math formulas. I and 2i, there is a map between, there is a hidden link between index I and 2i, right? Yeah. So the links are hidden. But we can control, right? Yeah. We can access all the nodes based on their relationships. Yeah. So it looks quite well, right? Yeah. The whole thing. Yeah. Then we can do the work. Right? So that's the data structure part. So we take care of the data structure part. Next, we need to work on the algorithm part. How do we arrange the elements in a max heap? And at the end, we want to sort our data in this array. Maintaining heap property. Because sometimes you may break the heap property, right? Sometimes when you do some change, you may get a violation of your max heap property. When that happens, we need to fix it. So now we look at the fixing part of the data structure. When the heap property is violated due to some operations, insertion, deletion, etc., how to fix it? Here, let's just look at insertion. We can fix it. And the work you fix the violation should be very fast. If you're fixing work, operation is not efficient, so then your whole algorithm is not efficient. So the work you need, it should be, binary. Log base 2 of n. This much amount of work, then it's acceptable. If the linear type, not acceptable. Binary type, it's acceptable. All right. Let's look at one typical triangle still between these 3 nodes. P, L, R, 3 closely related nodes. We want to fix the violation. Now we need to imagine there is some max heap violation occur in this triangle. We need to fix it. All right. Violation occurs locally in this triangle. And we assume the subtree with capital L as the root node has a max heap. And right subtree also corresponds to a max heap. Yeah. We only need to fix this local place between these, among these three nodes. All right. So we do local fixing operations. But after that, yeah, so you take care of the local part. After that, you can check for global violation. You need to make sure no violation occurs globally. So the last step, you need to do the global check. All right. Recursion approach. All right. So here for convenience, I use this recursion approach, but later we may need to change it. So this recursion thing, yeah, later, yeah, I need to, make some important comment about this recursion. Yeah. Here for our understanding, so let's use the recursion temporarily here. Yeah. Later, I need to make some important comment about this recursion way. All right. Now, so for this local triangle, 3 nodes, let me write a pseudocode. Do the violation checking, then violation fixing. 2 things. We need to use the pseudocode to complete these 2 things. First, the checking part. If A of I strictly less than A of 2i, then you get a violation, right? Yeah. Because it violates our max heap property. So you detect, this is a detection step. There is a max heap property violation right here between these 2 nodes. All right. Then you need to do some operation to prepare for next round fixing. The first round checking, right? First round processing, violation checking. Second round processing, violation fixing. All right. So the preparation. You store the index 2i to a temporary variable called the largest. You know the meaning. The meaning here, this temporary variable, you want to store the index that corresponds to the largest value among these 3 nodes. It's not a global largest, this local largest among these 3 nodes. Yeah. So now you store this 2i in this largest variable. Later you may update the value of this variable. Yeah. All right. So this is the detection, then preparation. The first line detection, second line preparation. Else, another case, A of I greater or equal to A of 2i, yeah, no violation, right? Yeah. Else part, no violation. No violation, you store I index in this largest temporary variable. Yeah. All right. So that's the left branch checking, yeah, because this is the left child node, right? This is left child node. So you do left branch checking. After it, you need to do right branch checking. This is how to check violation in the right branch. A of largest, now your largest could be I, could be 2i. If A of largest less than A of 2i plus 1, then you detect another violation, another possible violation. Okay? Yeah. All right. After you detect this violation, you need to do preparation. So you update the largest variable to 2i plus 1. Yeah. So this time you get a, larger value. So you store its index 2i plus 1 in this temporary variable for the detection part. Yeah, all right. So now you complete detection part. Next, the fixing part. Swap. You need to swap the values of two nodes to fix the max heap violation problem. All right. Before you do the swap, so you do another checking. If the largest not equal to I, that means the parent node does not hold the largest value among these three nodes. That means you need to do a swap operation. Yeah. All right. So then you do swap. You swap A of largest and A of I. A of largest could be left child node, could be right child node. Yeah, both cases, you cover both cases. Yeah. So you use one swap operation, you can fix the max heap violation problem within this local triangle. Yeah. So that's the, Then 8.4 heap example. So now let me show you a simple heap example. Yeah. All right. A max heapify example. All right. Here, because I do not have much time, so let me just complete this slide. All right. Here, in this example, you can see there is a violation. This place, there is a violation, right? Yeah. Because the values of child node is greater than the value of parent node, 14.7, both greater than 4. So here, I use the gray color on this node with value 4. Yeah. Here, so I call it a dirty node. Yeah. Because there is a violation occurs right here, starting with this node with value 4. So we call it dirty node. So we need to fix it. We need to clean it. Yeah, make it clean. Okay. All right. How to do it? Apply our local fixing operation. Yeah. So we swap, right? Swap. So we swap the values of these two nodes. After the swap operation, so we move the dirty node down, but it is still dirty, right? Yeah. We need to check this local triangle and see if there is any violation. Yeah. That node still not clean. So we need to do the local checking. Then we find another violation, we need to swap, right? Yeah. Swap the values of these two nodes. After the swap, then, because this dirty node, when this dirty node hit the ground, so this is the ground level, okay? Yeah. These nodes, that's the ground level. When the dirty node hits the ground, then we can make it clean. Yeah, because when that node reaches the ground level, no violation anymore, right? Because no child node below this node, then we can make it clean. So we fix that max heap violation with respect to this dirty node. One dirty node. So that's one dirty node. Yeah. Although you may need to check other places globally if you have other dirty nodes in your heap. Yeah. But you can see the way we check, we need to move down. When we move the dirty node down the tree, we follow a path to the bottom, right? Yeah. But another thing is, if you move down, if you check the local triangle, there is no violation. There is a possibility when you check the local triangle, there is no violation, then you make it clean. That dirty node, because if you detect no violation, you do not need to, to do the remaining checking. If any local triangle, after your detection step, no violation, you can stop. Okay, so you can stop operation with respect to this dirty node. But probably you have other dirty nodes, right? But for this particular dirty node, so you complete the fixing step. All right. So after this example, so we get to know our data structure, our heap data structure. So next, we need to work on the algorithm part, heap sort algorithm part. So for our Wednesday's class, for the first half, I want to complete the heap sort. So the second class, I want to start another topic, another advanced data structure. Part B, data structure. All right, so that's it. See you Wednesday.